Dear students, a very warm welcome to all of you. I think today's we are going to discuss about the crystal physics, which is one of the essential topic in your engineering physics course. In this module, we have to see in detail about the crystal structures, what are the various types of crystal structures and their properties, what is the applications of this crystal physics in engineering field. Yeah, these are all the modules we are going to discuss today's class about what are the classifications in crystal physics and what is mean by unit cell, because which is a fundamental one. What are the various types of crystals, basic types of crystals, how the atoms arrangement, that is called the Bravais lattice, Miller indices, and all the details of the crystal physics in detail we are going to discuss today's class. So basically you people know that what do you mean by a solid, a solid which is made up of an atoms in which the atoms which are closely or tightly packed. In this one, solids which are mainly classified into two categories, namely crystalline and amorphous solids. And what is the difference between the crystalline and amorphous, we can see here. And what do you mean by the basic or the unit cell of a crystal, and what are the 7 basic fundamental crystal systems we are going to discuss. So you see the difference between these two. As you all very well know, what do you mean by a crystalline, what do you mean by a non-crystalline solids. Crystallines, can you see the diagrams? You see the atomic arrangement, it is a regular array of atoms. So that is meant by a crystalline solid. The amorphous, non-crystalline material. Here the atoms, irregular array of atoms, or the atoms are arranged in an irregular manner. Crystalline materials, so you can classify it as a bulk single crystals or a polycrystalline materials. Here generally it is amorphous, means it is a non-crystalline materials. You see the examples, iron, silver, gold, like this. These are all the examples for crystalline materials. For a non-crystalline, can you see the diagrams? Glass is a non-crystal, rubber and plastic materials. Can you see what do you mean by a crystal? It is a definition is given. Crystal is a three-dimensional solid which consists of a periodic arrangement of atoms. So, and what do you mean by a crystallography? It is a field, you can study in detail about the crystal structure and what is the properties of crystal in detail about this crystallography. So can you see what do you mean by a crystal structure, which is a formation of lattice and basis? Can you see the diagrams? A lattice, which is an imaginary point in which an atom or a molecule is there. What do you mean by a basis? Means it is nothing but a number of atoms or molecules which are oriented in each lattice point. When you combine both lattice and basis, it forms a crystal structure. Yeah, now you know the basic definitions of a crystal. You know that. What do you mean by a crystallography? Now you know that. What do you mean by a lattice? Lattice is nothing but it is a representation of an atom which are oriented in x, y, z directions, generally which is called a space. The lattice points which are equally arranged, these are all the array of points in space, in x, y, z directions, which is called the crystallographic axis. So the individual points in a space is called lattice points, in which the atoms or molecules which are oriented, and basis are nothing but this is a crystallographic term. Here basis means how many atoms or molecules which are oriented in each lattice point. Can you see this is the fundamental of crystal physics, unit cell. So unit cell means in our body, our cell, organism cell is a basic, which is a building block of our organ. Similar way in a crystals, in solids, these are all the unit cell, which is a basic or a fundamental units, which is repeating in space x, y, z direction, which forms the crystal lattice. Can you see the different types of orientations of unit cells in various, you can represent either it may be a square, it may be a rectangular. So it is a repetition of the same unit cell in x, y, z direction, which forms the space lattice. Can you see the arrangement of atoms in a unit cell? So how should be the unit cell which is arranged in different orientations? It is like a two-dimensional representation, So like this, unit cell, as I told you, which is the smallest or fundamental unit of a crystal, which repeats in x, y, z axis, which forms the space lattice. So it is a representation, no? This diagram which shows how the unit cell which is represented in XY direction, that is called a two-dimensional direction, as well as can you see the diagram of a unit cell in three-dimensional view, it is XYZ direction. Now which is an essential one. What do you mean by a lattice parameter? Means parameter, it is a set of physical quantity which represents, you can identify the crystals based on the lattice parameter, which is nothing but two components, namely axial length and interfacial angles between the crystallographic axis. Can you see here ABC is the intercept values or axial length along X, Y, Z direction, as well as can you see the interfacial angles, alpha, beta, gamma. It is the angle between the three crystallographic axes, example YZ, ZX and XY. So based on this lattice parameter, we can classify the crystals, 7 basic crystal systems are there based on the lattice parameter, namely cubic, tetragon, orthorhombic, monoclinic, triclinic, rhombohedral or trigonal and hexagon. These are all the 7 basic crystal systems. Can you see the simplest form? No? The first one is a cubic. You know how the cubic is formed. The axial length or the intercept values which are equal ABC, and you see the angles between the three crystallographic axes which are equal, which are mutually perpendicular to each other. Alpha, beta, gamma value is 90. So can you see the other one? It is a tetragon. It is same, when you cube one of the length you can increase. For example, AB, you keep it as it is. When you see the length, C, which is not equal to A and B, but the interfacial angles which are equivalent to 90, this type of crystal system we call it as a tetragon. The next one, which is an orthorhombic, can you see the axial length which are not equal, but you see the interfacial angles alpha, beta, gamma which is equivalent to 90. So this is one of the crystal structure. See the monoclinic, all the axial length which is not equal, and can you see the alpha, beta, any two angles which is 90, and in this diagram which is one of the angle, which is alpha is not equivalent to 90. One of the angle, either alpha or beta or gamma is not equal to 90, which forms the monoclinic structure. And next one is a triclinic. The axial length or the intercept values ABC is not equal to each other, and also the interfacial angles alpha, beta, gamma which is not equivalent to 90 and not equal to each other. Next one we see the hexagon. So here the A and B which are equal, the axial length C which is not equivalent to A and B, alpha, beta exactly 90 degree and gamma is exactly at 120 degree, which forms the hexagon. This is the last of this 7 basic crystal system, which is called rhombohedral. We can also call it as a trigonal. Here the axial length, ABC which are equal, and alpha, beta, gamma also equal, but the angles are not mutually perpendicular. All the angles are equal to each other but not 90 degree. You see, as we discussed above, these are all the 7 basic crystal systems which axial length and interfacial angles which are known as the lattice parameter, and the examples for each crystal system is given in this table. Next one we will see about the arrangement of atoms in these basic 7 crystal systems, that is called Bravais lattice. Here can you see the point group operations? There are basically 7 crystal systems are there. Within this 14 ways of arrangement of atoms, possibles, that is called Bravais. Auguste Bravais, he is the name of the scientist. Based on this, we have 14 crystal systems are there. Can you see how the atom arrangement, that is the arrangement of points in space, we may get based on the 7 crystal systems, we can derive 14 ways of arrangement of atoms in 7 crystal systems. Can you see here, for example, you take a simple cubic structure. The Bravais lattice which are possible is 3. One is a simple. Simple is nothing but the atoms which are oriented at the corners of the atoms. Body centered cubic, as you know, one atom is at the center, remaining 8 atoms at the corner, because cubic is 8 corner. Face centered means there is an atom which oriented at the center of each face. There are 6 faces in a cubic. Similarly, tetragon, you have 2 types. One is a simple and body centered. Orthorhombic, which contains all types of Bravais lattice, that is, a simple is possible. Base center means one atom which is present at the base of bottom and top, as well as body centered, as well as face centered. All the four Bravais lattice are there here. Monoclinic you have a 2, simple and base centered. The remaining triclinic, rhombohedral and hexagon, they have only simple cubic structures. When you add all, no, you may get 14 ways of Bravais lattice. So now we will see in detail about the cubical cell. So cubic systems, as you know, the lattice parameter is ABC is equal, and the angle between the in axis alpha, beta, gamma, which is equivalent to 90 degree. So can we see, discuss here in detail the number of atoms per unit cell, coordination number, what is our atomic radius and atomic packing factor. Number of atoms means how many atoms which are present inside the unit cell we can calculate. Coordination number is nothing but you take any reference atoms, you calculate how many number of equidistant atoms that particular atom has in a structure. You can calculate atomic radius is nothing but it is half the value of the interatomic distance, and atomic packing factor, which is nothing but a ratio, the volume occupied by the atoms within the unit cell to the total volume of the unit cell. We know that a cubic, which has the 3 Bravais lattice, namely simple cubic, body centered cubic and face centered cubic. So we can see all the characteristics. So how many atoms per unit cell, how many equidistant atoms has this cubic, atomic radius we can see, and we can discuss about the packing fraction. Yeah, this is the simplest form of a simple cubic. Can you see here ABCs are equal, alpha, beta, gamma is 90. Okay, so this is a one unit cell. You can find the diagram which shows each corner atoms. There are 8 unit cells which are represented in this diagram to calculate the equidistance. The first characteristics of this simple cubic is each corner of a unit cell, the atoms which are oriented at each corner, which already discussed. The simple cubic means 8 corner you have, all the atoms, each atoms which are oriented at the corner. So you see here, this is the actual 3-dimensional view. The atoms which are present inside, can you see the diagram? You take only one corner, the atoms which is not entirely present inside, which is shared by 8 unit cells. So that what is the volume present inside the unit cell means, you take a one atom which is divided by 8 unit cell, because 8 unit cells are sharing this particular atom. So the total number of atoms within the unit cell, how can you calculate means 1 by 8 is the volume present inside into how many corner atoms? 8. So that 1 by 8 into 8, so it is the 1. So total number of atoms inside the unit cell is only 1. As you know, this is the 8 unit cells, So how can you calculate the coordination number means you take the center one, which is the equidistance of 4 in the same layer, 1 in the top side and 1 in the bottom side, so that there are 6 number of atoms which are equidistant. Hence the coordination number for simple cubic is 6. Then can you see the coordination number, how it is represented? 1 in the top, 6 in the bottom, that is the top and bottom which is represented here. The atom is 1 and 6. 2, 3, 4, 5, you see, which are in the same lane, same plane. From the reference atom is that is one of the corner of 8 unit cells. Here which is represented by a violet color atoms. So you take that is your reference atoms. So the coordination number is 6. Can you see the next one, which is atomic radius we have to calculate. We know that what do you mean by a nearest neighboring distance, which is the interatomic distance, which is the distance, shortest distance between the center of any 2 neighboring atoms. Can you see here it is an A. A means it is a lattice, it is the distance between the center of 2 adjacent atoms. So that which is nothing but R plus R. So A is here, it is a 2 or twice the distance. Hence atomic radius is half the distance between the 2 nearest neighboring atoms. So when you divide A by 2, it gives the atomic radius. Yeah, similar way the body centered cubic means, can you see here, one atom which is present at the center, remaining 8 which are oriented at the corners. This is a 3-dimensional view of the body centered cubic. Yeah, each corner atoms, each corner of a unit cell, one atom is present. So total corner is 8. So that 8 unit cells which are present. Apart from this, one atom which is present at the center of the unit cell. So how can you calculate the number of atoms means? What is the number of atoms which are present means? Corner means, as you know, we are discussed in the previous slides, the sharing is 1 by 8 because the corner atom which is shared by 8 unit cells. So the volume present in each unit cell is 1 by 8 into number of corner atom is 8 corner atom plus 1 is present at the center. So 1 plus 1, the total number of atoms present in this BCC, body centered cubic, is 2. You see the coordination number which is simplest, how many equidistance. Can you see the diagram here, which you can easily understood. One atom is present at the center, you take it, it is here, it is blue. Then the remaining, corner atoms which are in represented here, it is in pink color. Can you see all the 8, which are equidistant with respect to the body centered atoms. So the coordination number is 8. Can you see the three-dimensional view of a face-centered cubic structure? The same, lattice constant, that is the lattice parameter, there won't be any change for a simple cubic or a body-centered cubic and face-centered cubic. Can you see here? ABC and alpha, beta, gamma, there won't be any change in all the 3 types. Only the orientation of atom is changed. Here, it is a face-centered means there is 8 corner atom is always there. Apart from, you have a 1 atom which is present at each face. So how many faces in a cubic? So that 6. So 6 face-centered atoms and 8 corner atoms which are oriented in this structure. Yeah, can you see here how it is calculated? Each corner, you know that 1 atom is present, so that 8 atoms are oriented at the corners. One atom, face-centered atoms is 1. So the face-centered atom in a face-centered FCC is there is a sharing, which is shared by 2 unit cells. That is the half the volume present in one and half the volume of the atom shared by the neighboring unit cells. So that 1 by 2 is the sharing of face-centered. So 1 by 2 into, we know that 6 face-centered, 1 by 2 into 6, so that 3 atoms plus 1 by 8, that is the sharing of corner atom into 8 corner. So that 1 by 8 into 8, it is 1 plus 3, totally 4 atoms are there in a face-centered cubic. The reference atoms which are blue and then equidistant atoms which are represented here as a yellow. Each phase, when you take x, y, z plane, each plane there is a 4 face-centered atoms are there. X plane 4, y plane 4 and z plane 4. 4 plus 4 plus 4, totally 12. Yeah, can you see here now the number of atoms for a simple cubic 1, body centered 2, face centered 4. Coordination number, can you see equidistance 6, 8, 12 respectively. The atomic radius for here, it is R is A by 2, and for a body centered cubic it is root 3 by 4A, and face centered cubic it is root 2 by 4A. The atomic packing factor, can you see 52% volume occupied, 68% and 74% respectively. 74%, it is more closely packed. So if more number of atoms are there shared here in this FCC. So can you see the example? Polonium is a element which contains this simple cubic, iron, barium like this, which is an example of a body centered, and generally conducting elements like a copper, aluminum, these are all face centered cubic structures. Now we can see the Miller indices. Miller indices which are nothing but we can identify the planes in a cubical structure. Can you see a simple cubic? As you know, A, B, C are equal, alpha, beta, gamma is a perpendicular one. Here we can identify the planes. Can you see here the plane 1, 0, 0 means? Can you see the intercept? How can you calculate means? First you find the intercept along x, y, z axis. So it is 1 time in A, and the intercept values are you see the plane which is shaded as a blue color line, which is parallel to the y axis and parallel to z axis also. So if the plane is a parallel, you know that there is the intercept is infinitive, so that it intercept along the x axis at A y-axis at infinitive b and infinitive along the c-axis. So you take the coefficients of the intercept along a, x, y, z. Can you see the coefficients? 1, infinitive, infinitive. So you find the reciprocal of the intercepts, because the reciprocal of the intercepts are nothing but Miller indices. So reciprocal of 1 is 1, reciprocal of infinity, 1 by infinity, you know that 0, and along the z axis 1 by infinity is 0. So Miller indices means you take a bracket, within the bracket there is a space between the index values of 1, 0, 0. It means that the plane cuts x-axis at 1, the plane is parallel to y and z axis. So these, how can you find the Miller indices? First we will see the definition. It is a set of 3 numbers, as we saw the previous slide. It is a set of 3 numbers which designate the plane in a crystal. It is a set of numbers which are known as a Miller indices, which are nothing but the reciprocal of the intercept which are made by the plane on the crystallographic axis x, y, z. So when you find the numbers, then you find in a smallest whole numbers by taking LCM. Finally it is known as a Miller indices. So how can you find the Miller indices? There are various steps are there. You see the step 1, to find the intercept along made by the plane first. Step 2, to find the coefficients of the intercept. So you take a step 3 is the find the reciprocal of the coefficients, that is the numbers. You find the reciprocal of the coefficients, convert the reciprocals into a whole number by multiplying each other, which is the reciprocals with their least common multiple. Take an LCM to convert these reciprocal into a whole number. Enclose these numbers in a bracket which shown in the slide, that forms the Miller indices. These are all the ways to identify the Miller indices in a given plane of a crystal. Yeah, this one which is already discussed, 1, 0, 0 plane can be calculated like this only. You see 1a, infinitive b along the y-axis and infinitive c along the z-axis. So the intercept value, it cuts x value, x-axis at 1, y-axis at infinitive, similarly z-axis at infinite. Then you find the reciprocal of the coefficients, then that gives the Miller indices with brackets. Can you see the similar way in a simple cubic structure? Previous we saw there 1, 0, 0. Now can you see here the plane which cuts the y-axis at 1. So the plane is parallel to x and z, so that 0, 1, 0, because that is the Miller indices along the y-axis. Similar way, can you represent, see the plane? The plane which cuts the z-axis at 1, so that the plane is parallel to x and y. You can easily identify it because the intercept which are infinite at a and b, the plane cuts z-axis exactly at 1, so that the Miller indices are 0, 0, 1. Like this, this is the second set. If any two index values are there or the intercept values, you see the plane, what is the shape of the plane? Can you see here? The plane which passes through the diagonal of the cubic. The plane, for this example, you take an crystallographic axis xyz of a cubical structure. This plane, it cuts x at 1 and y at 1. Can you see it passing through the diagonal? The plane is parallel to z-axis, so that coefficients are x-axis 1, y-axis 1. It is parallel to z, so that the coefficient is infinitive. So can you find the reciprocal? 1, 1, 0. So when you, with brackets, you can represent this reciprocal number, which means that that is the Miller indices of this plane 1, 1, 0. Can you see here? This is another example. You see the plane. What is the shape here? Previous, it is the first one 1, 0, 0 is a square. 1, 1, 0, it is a rectangular type. It is a two-dimensional representation. Can you see the plane 1, 1, 1 in a cubical structure? The plane which cuts x at 1, y at 1 and z at 1. So all the values, 1, 1, 1. these are all the coefficients of intercept along xyz axis. You find the reciprocal of the coefficients, it again becomes 1, 1, 1. So you within the bracket you can represent, that gives the 1, 1, 1 plane in a simple cubic structure. Yeah, this is another type. You can draw the various forms of Miller indices. You see the similar, it is similar to 1, 1, 0. So, but what is the plane here? Can you see the intercept along the x-axis? The plane cuts exactly middle of 0 and 1. So, you take half, that is 1 by 2 along the x-axis, and the plane cuts exactly at 1 along the y-axis, and the plane is parallel to z-axis. So, 1 by 2, 1, infinitive. These are all the coefficients of intercept along x, y, z. If you take the reciprocal 2, 1, 0, you express in terms of brackets, that shows a 2, 1, 0 plane in a cubical structure. Similar way, you can the next set, can you can practice more number of planes in a cubical structure. Can you see here, you can easily identify the plane which is parallel to x and y. It cuts z-axis exactly the middle, that is 0, 1, in between 0 and 1, it is nothing but 1 by 2. So, the plane is parallel, as I said. X and y, you take the coefficient is infinitive, the intercept value, coefficient value along the z-axis is 1 by 2. So, the Miller indices is 0, 0, 2. Yeah, these are all, you can, how can you identify 1, 0, 0 in a plane, 0, 1, 0 and 0, 0, 1 in all planes, which contains only one index, that is h, k, l, h alone, second one k, third one l. So, like this, if any index value is 1, the shape of the plane is a square. Now, you plot the Miller indices diagram for 2, 1, 2 plane. So, Miller indices values which is given, you find the reciprocal half, because 2, 1, 2 the Miller indices is given. So, how can you draw the plane? Based on this, the plane cuts x-axis at half, y-axis at 1, z-axis at half. So, all the three values means definitely the shape of the plane is a square triangle. You draw the triangle inside the plane with the given index value. Yeah, next we will see the what are all the various types of defects, defects in crystals. These are all the imperfections in crystals. So, because as you know, the crystal which is a regular geometrical arrangement of atoms, as you know. So, here you can see the various types of defects, particularly these types of defects are called zero dimensional defect. In this diagram I am explaining all, either the regular site there may be an atom is missing, which is called the vacancy, or the atoms which are can occupy in an interstitial site, there is an interstitial defect, because without affecting the regular structure, or due to some of the doping, impurity atom or the substitutional impurity is added to the pure form. So, these are all the various types of crystal defects in crystalline solids, mainly for zero dimensional defects. There is different classifications of defects. Zero dimension, that is a point imperfection, line imperfection and surface imperfection, which is nothing but two-dimensional defect. Can you see here, there is a defect in a particular point, that is in a regular array of atoms, there may be atoms are missing. This is called a point defect. Line means there may be a few atoms which are missing in a particular lattice line, which is called the line defect. Surface means there is a missing of atoms in any two dimensions, either xy or yz or zx. So, this is called two-dimensional surface defects. You see the various types in defects. Point imperfections, vacancy is a point imperfections. Within that we can having a Frenkel and Schottky defect, and then interstitial defect, self-interstitial or foreign impurity atoms or doping. Then line defects, you have a two types of defect, edge dislocation and screw dislocations. These are all the line defects in crystal imperfections. Surface defects, you have a grain boundary, tilt or a twist boundary. Twin boundaries you can explain in detail, and stacking fault. These are all the different types of defects in crystals. Can you see the defects, various types of zero dimensional or point imperfections, line imperfections and surface imperfections. Can you see the crystal defect? There may be a missing of an atom in a regular orientations, or there is a various types of point imperfections. As you know, a vacancy is a point imperfection, interstitial defect and impurity defect, that we see in detail. It is a regular array of atoms. There may be a missing of an atom in the regular crystal structure, which is called the vacancy. So vacancy, interstitial also, there may be atoms, the atom size may be a very smaller one, which can occupy the void space without affecting the regular crystal structure. Both are vacancy or interstitial. Here can you see the interstitial means, can you see here NaCl? No, can you see the example of a NaCl, ionic solid Na plus Cl minus? The placement of ions in a crystals, it may be, seems to be like this. Types of vacancies, vacancy defect is either the Frankel or Schottky. Can you see here Na plus which is an cation, Cl minus which is an anion. When an atom or a smaller ion, usually smaller ion is a cation, it leaves its place in the regular lattice and creating a vacancy is called Frankel, which does not have any impact on the density of the solid, as it involves only the migration of the ions within the crystals. Can you see the diagram? This cation which migrate to some other without disturbing the crystal structure, which is known as Frankel defect in sodium chloride lattice. Can you see the Schottky? There is an equal number of cations and anions are missing from their lattice sites, so that the electrical neutrality as well as the stoichiometry is maintained. This type of a defect which is called the Schottky defect. So this is an example for both. There is a mismatch, Frankel defect, missing of cations and missing of both the cation anions. So both are giving here a Frankel defect as well as Schottky defect. So can you see here the difference between the Schottky and Frankel defect? It is due to the missing of ions. Usually the cation is missing. Here it is due to the equal number of cation anions are missing in the regular site. It has no effect in the density of the crystals. As a result, there is a decrease in density of the crystals because a pair of ions are missing. Frankel defect are found in highly ionic compounds. Here it is found in crystals with a low coordination number. Can you see the example? Sodium chloride is an example for the Frankel defect. Here it is for this zinc sulfide. Yeah, this one point defect is over. Next we will see the same interstitial. It is again one of the point defect. So here what does it mean? Means there is a impurity or a foreign atom. So foreign atom which occupy the interstitial site of the regular crystal structure without disturbing, which is called self-interstitial. So the same atom which can occupy in an interstitial site, or this is due to impurity atom, that is a foreign atom can occupy in the interstitial site. So that interstitial you can have two categories. One is the self-interstitial, the other one is a foreign interstitial. The same atom which occupies at the interstitial site, the impurity or the foreign atom which occupies the interstitial site as shown in the diagram. Can you see here? Substitutional. It is again one of the point imperfections in crystals. Substitution. Can you see here? There is a impurity atom which occupy the regular lattice site, either depends on the site of the atoms, which is either without affecting or some of the, can you see the diagram, the atomic radius is slightly larger than the regular site, so that it will disturb the crystal structure. So this type of impurity is called substitutional impurity. So in this diagram, self-interstitial, substitutional impurity and interstitial impurity all are shown here as a point imperfections. Yeah, can you see here which type of defect can you identify? What are the various types? What is the vacancy defect? Now you can easily identify what is an interstitial, which is due to foreign impurity atoms. Like this, what is a substitutional impurity defect? All are can be given as an example here. What do you mean by Schottky and what is a Frenkel? No, now you identify the ionic defects in crystals. Yeah, next we will go to one-dimensional defect, which is an edge dislocation and screw dislocations. There are two types. Can you see here? What do you mean by it is an one-dimensional defect or a line defect? Based on this, point imperfections or point defects, as it is a zero-dimensional defect in crystals. Here we are discussed in detail about the vacancies. What is the vacancies? What is the ionic defects like a Frenkel and Schottky? And what are the interstitial, that is the self and foreign, and what is the interstitial or impurity defects we discussed in detail. So today's class, I think you are all having a clarifications about the crystal physics. So what do you mean by a crystal? What is the difference between the crystalline and amorphous solids? So what are all the lattice parameter of a crystal? So based on the lattice parameter, what are the various types of crystals, like 7 crystal systems we saw there in detail. So based on the 7 crystal systems, we can see the arrangement of atoms in 7. What are all the 14 ways of possible arrangement of atoms in 7 basic crystal systems, that is known as a Bravais lattice. So how to calculate the crystal terms like atomic radius, coordination number, like this, atomic packing factor, all we can see, and what are all the different types of defects in crystals, mainly what is point defect, line defect and surface defects. In detail we are discussed about the point defects in crystals. Thank you.